Hi there and welcome back. Let's add a quick bit to our discussion of nested loop join and thus complete our discussion of this very important core join operator that is present in any relational database system because it's the fallback that has very few restrictions regarding its execution. Actually, the predicate is arbitrary. There is no considerations regarding sort order or the outer or inner. There are no strict considerations regarding working memory that has to be available. It's really the fallback that we can use all the time. But this doesn't mean we cannot tune and improve it. One such tuning, one such improvement I would like to discuss in this brief and short video with you before we call it a day regarding our discussion of nested loop join. Alright, so this is the original nested loop join as we've introduced it. And if you have a look at the inner loop here, the inner loop, what's the purpose of the inner loop? Given one particular O value, given one binding for the row variable O, these bindings are, of course, generated outside the inner loop. Alright, so from the viewpoint of the inner loop itself, O, the current row O, is indeed a constant in a sense, right? We fix one O here, O has been bound, the row variable, and then we enter the inner loop. During the execution of the inner loop, O is a constant. Okay. Inside this inner loop, we are on the search for all the rows that can, that can satisfy this particular condition. But indeed, this condition is a comparison of the current row I against a constant O. Okay. And then of course we loop over all the rows in inner to find all the matches and so on. This view of nested loop join, where I look at this inner box here and regard O, the binding for the outer row, as a constant, suggests a different evaluation strategy, a different evaluation mode for index nested loop joins. Well, if you look at the inside of this box here and O is regarded a constant, what you have here is a crude description of an index scan. Given the entries in one particular index, in this case, this would be the role of the inner table, try to find all the rows I that compare to one particular constant or index lookup value O in the theta relationship. Find all these rows I and then append them, or append them to the output. This is what an index scan can do. And indeed, there is a variant of nested loop join, the indexed nested loop join, that does exactly that. So let's quickly switch over to this. It's slide 10 here that I've jumped to. All right, so the index nested loop join. This may speed up the vanilla nested loop join considerably. Instead of repeatedly scanning the inner relation, we will have repeated index scans on an index that has been built on inner. Of course, the index has to be able to support the theta comparison relationship. Okay, so that would then be the setup of the algorithm. It would still be a nested loop join and it would still receive the three same arguments. So the API wouldn't change, but the internals would change. All right. We would of course perform the iteration over the outer. So for the outer, nothing has changed. No considerations, no restrictions, no constraints on the outer table here. What is completely different is the inner loop. There is indeed no inner loop. There's only repeated index scans, maybe even index-only scans. There are repeated index scans. So we would scan an index I, an index that has been built on the inner table. And this would be the index condition. This would be the index condition. Recall that inside this inner loop, O is indeed a constant. Okay, so this is a regular index condition as we have discussed them when B plus trees were on the table. We are looking for rows that are stored inside our index that are in theta relationship to the constant O. This is a regular index condition. For all of these rows that the index scan can deliver, maybe it cannot find any row, maybe it can deliver many rows. For all of those rows I that the index scan can deliver, well, we will append O, I, the current O and the just found I as a pair to the join result. And that's about it. So all the iteration that has been performed in the inner loop is now implicit in this index-only scan. Of course, some iteration is happening inside the index scan, but a much more targeted iteration. An iteration that will only find those rows that indeed fulfill the join condition, which has turned into an index condition here. All right, so that's the general strategy of an index nested loop join. Certainly the best case that we have discussed so far. Okay, so we have discussed why O can be considered a constant when we invoke the index scan, maybe even the index only scan. It depends on the width of the result that we are going to produce in this particular join. And well, of course, index I has to support this particular predicate. So if this is a predicate like O less than in a row or O less than or equal in a row, it's clear that we need an index I that is indeed an ordered index, for example, a B plus tree. Well, if the ordering criterion of the B plus tree is compatible with this particular index condition, then index nested loop join is the nested loop join strategy of choice, of course. And indeed, the index scan will only deliver actual join partners for O. Okay, so that's the best case that we can hope for. Here is a graphical depiction of the entire scenario. So now what is participating, of course, is the outer table and no changes there. This is just some random outer table that we will scan in the outer loop as before. Probably we are going to use a sequential scan there. There's, of course, participation of the inner relation. Okay, right. But, well, instead of iterating over all entries in the inner relation directly, we will use the index I to navigate to the potential join partners inside the inner relation directly. All right, we will have repeated index scans. So let's look at the sample query that we are going to evaluate here. Well, there's of course the one and many tables, and the rows have been assigned as being outer and inner in this fashion. Okay, so if this is a condition, a join condition, that should turn into an index lookup condition, well, then we are looking for an index support on either outer or inner that can support such comparisons here. We have just constructed an index on the inner on many, as you can see. The index I has been constructed on many on the join column A. Okay, this turns this particular predicate into a viable index predicate. Is the join predicate here, but it will turn into an index condition if we consider O.C as a constant. All right, so then the index condition will read MA less than constant, index I, the ordered index on the column A of table many, will be able to support this particular index condition. All right, so this is what will actually happen. We will scan over the rows of our outer table. We will consider O0, then O1, then O2. But let's say we are currently considering O0. For this row O0, which is now held constant, we will perform an index scan. We will perform an index scan on index I and use O0.c as the constant that we are using in an index lookup. This constant will directly lead us through the index to the particular hit here. And either we would look for this particular hit and then perform an index backward scan to find all the hits here, all right, because we are looking for all the rows whose A value is less than O.C. Well, or we would just descend at the very left of the tree here and hit the sequence set at the beginning. So from the beginning of the sequence set, we would just scan the sequence set and would end the scan when we hit this particular point in our sequence set when the A values of the many table of the inner relation exceed O0.c. Okay, well, of course, for each such O, for each outer row O, we would perform one such index scan, but it would immediately lead us to the join partners that we have to emit during this particular join. Very efficient. Okay, I think we can very nicely see that over there on the terminal. So let us see. So let's recall let's recall the indexes on the many table, because they become relevant now in our experiments here. So let's do that. Right, so this is the many table. If you look closely, yeah, then you can see that there is an AC B tree index on the inner table. Why is that? Well, it's the primary key index that has a leading column A, which will be relevant here, and the column C as a secondary column in the concatenated key here. Okay, so now let's look at the query that we've just seen on the slide. It's actually a verbatim copy of the query that you've seen on slide 11. I have added this conjunct here, which is just a local condition on the one table. It's not a join condition. It's simply here to keep the results smaller and more manageable. So this is not related to join evaluation at all. What is related to join evaluation is this join predicate, of course. And as you can see, it's a comparison on the A column here, on the A column, less than comparison on the A column. There is indeed an index on the many table that can support this particular condition, and it's of course this particular B tree. We have learned that well, this index condition fits this particular B tree if the participating columns here are a prefix of the concatenated key of the B tree. The concatenated key reads AC in that order. MA is a prefix of that. That would be a proof that this B tree, the many _A_C B tree, can support this particular join condition, which will of course turn into an index condition. Regarding the one table, well, in the join condition here, we have a participating column C. There is no index on the C column in the one table. So if we consider index nested loop join for the evaluation of this particular join, then only the many table can play the role of the inner table. Only this table has an index defined on it that could help in the evaluation. All right, so let's see whether we can indeed observe PostgreSQL while exploiting index nested loop join. All right, evaluating the query. I think it's time to have a sip of coffee here. Very nice. Why don't you go and fetch a coffee? The query takes a while, it appears. Well, it should be over soon. So, oh, there we go. All right. Right. Okay, so let's have a look at the plan. All kinds of cool details regarding JIT compilation here. This is currently not the focus. All right. So, well, yeah, of course, there is a nested loop join. Right. There is no indication that this is an index nested loop join. But if we look at the inputs of this nested loop join, we can clearly see that this is indeed an index nested loop join. There is the outer input, which is just a sequential scan over the one column. All right, so the outer input is treated as is. As before, we simply scan the outer input once. Okay. While we do that, we have the opportunity to evaluate local predicates. This is just the predicate to help keep the results smaller. All right, right. It does not influence the evaluation of our join. So that would be the outer input. The other input indeed is an index scan. This turns the entire construct, the entire nested loop, into an index nested loop. All right, so this combination of nested loop and the index scan on the right hand side on the inner input turns this combination of operators into an index nested loop join. Okay, of course the index scan is performed on the many table, which would be the inner table here, and as you can see, indeed the index condition directly reflects the join condition that we have seen above here. Let's keep in mind that O.C here is indeed a constant, just a constant, a normal constant that is fixed whenever we enter this particular index scan. All right, so that would be a regular forward index scan in this particular case for some constant value here. All rows that are less than this constant value will qualify. It's just a normal left to right scan of the sequential sequence chain. I'm sorry about that. Until we hit the OC border value here. And as you can see, indeed, this index scan is performed many times. For each of the outer rows that can contribute here, this index scan is performed. It's performed 6,249 times. Does this make sense? I think it makes sense. The one table has 10,000 rows. 3,751 of these have been removed by this early filter. So that leaves 6,249 outer rows that we have to consider, and that many times we will perform index scan. Well, I would rather choose to perform 6,249 index scans than to rescan the inner loop, the inner table, in this case the many table, that many times over and over again. All right. Oh yeah, one thing I would like to note is that indeed the index, the join condition here, the join condition above has indeed turned into an index condition. When we now scroll up to the nested loop join, what you will see here, what you won't see here, is an extra join condition entry at the nested loop. Indeed, all the necessary predicate evaluation and all the removal of the potential non-candidates for the result tuples have already been removed by the index scan here. There is no residual or extra predicate evaluation work to be performed by the nested loop. No mention of any join condition or some above here at the nested loop operator. Compare this to the nested loop operators that you have seen in earlier experiments. All right, so indeed, the index scan only delivers hits. It's the best case that we can hope for. Right. Well, there's one word of warning here. One word of warning. This would be a query that reads very similarly. It's a join between the one and many tables. Okay, that's interesting. So there's index support on the one and many tables. Maybe we can use index nested loop join. Grust said, well, if there is a nested loop and an index scan in the resulting plan, then we are looking at an index nested loop. And well, that's true, but only if the index scan is indeed placed at the correct spot in the resulting plan. So this would be a query that looks like the query above, and it will feature a nested loop and it will feature an index scan, but this is not an index nested loop situation. So this is just a caveat. Let's quickly look at that. Well, there's again such a local predicate here that helps to keep the overall result small. So this is not related to the join evaluation. This is just a predicate on many. Okay, so that's fine. This is the real join condition. It's well, it's specified on the C columns. On the C columns of the many table and the one table. Well, the C column in the one table is not index supported, so that much we know. The C column of the many table, well, that was mentioned in an index definition, right? So let's look at that. Oh yeah, there it is. Well, but it's not a prefix of this concatenated index key, so we cannot use lookups just based on the C column. We cannot use this B tree to perform efficient lookups just regarding the C column, right? Hits will be distributed all over the sequence set of the regarding B plus tree, that it will be of just no help. All right, so let's see how this query is planned. Right, okay, some waiting time again. I've got more coffee, yeah, that's nice. All right, so there we are. And what you see is an index scan. Oh, that's nice. It's even placed in the inner. It's even placed in the inner of a nested loop join. So index nested loop join. No. Let's have a closer look. Okay, nested loop. This is at the left-hand side, the outer input. The outer is still the one table. Okay. The inner is indeed this many table. Okay, so the situation is as above. But as you can see, there's this materialize operator here. There's this materialize operator, and this sits above the index scan. If you look closely at this index scan, of course, it has an index condition. Any such index scan has to have an index condition, but this is not the join predicate. This is not the join condition. This is just the local predicate on the many table. The local predicate is referring to the A column, the B plus tree that we've just seen. It can support this particular local predicate, and this is exactly what happens here. We evaluate the local predicate using the index scan. We will then materialize the resulting rows so that they are ready to be iterated over many times, indeed 10,000 times. Okay, right, so this is not a repeated index scan, it's a single time index scan to just evaluate the local predicate. You see, it's not an iterated index scan, it's just performed once. It delivers the rows so that Materialize can hold them in a tupper store, ready for the evaluation of the nested loop. And it's still the task of the nested loop join to evaluate the join predicate. And we should even see that buff here. Well, yeah, there's the join filter. Nothing has helped the join to perform this predicate evaluation. It still has to do it on its own. The index scan has been used to evaluate this local predicate on the many table only. This is just a caveat that you have to look closely to detect that the combination of nested loop and index scan indeed makes an index nested loop join. All right, so that concludes our discussion for now for index nested loop join. We will come back to joins in the constellation of larger plans in a future chapter, but in this chapter we will now turn to other types of joins. The next up, I think, is merge join. I hope you will be around when we tackle that. See you then. Bye-bye.